Hello everyone. In this lecture we will be discussing about design of DC-DC converter. So far we have learned about the current voltage relationship, and now we will be designing the passive components of it. The most important part of a DC-DC converter is actually the inductor, which acts as a current storing element and actually energy storing element. In one part of the cycle, the inductor gets charged, and in the other part of the cycle it gets discharged. We have to remember that we have to operate the inductor in continuous conduction mode. That is, some amount of current must flow through the inductor at all the time. The current through the inductor must never be zero. And continuous conduction mode reduces the peak and RMS current compared to the discontinuous conduction mode for the same output power. That is, output power being the same, the current consumption or the peak currents in the continuous conduction mode is less than discontinuous conduction mode. Since the peak current are less, there is less spike and all the components are saved, and the efficiency also increases. Now, as we have seen that in case of DC-DC converters, the inductors at one part of a cycle gets charged and at the other part gets discharged. So here we can see for the first part, the current through the inductor rises and the inductor gets charged, and when the switch is off, the inductor gets discharged, and as a result we get this like a zigzag pattern in the inductor current. Now this zigzag pattern has an average value. We consider that average as IL. Now and the change in the value of the current, we consider it del IL. So this point, this is the minimum current point. This has to be IL minus half of del IL. And for continuous conduction mode of operation, this point cannot be equal to 0 and cannot be less than 0. So it has to be greater than equal to 0. So this is our condition based on which we will be designing all our DC-DC converters. Another thing we can remember is VL is equal to LTI dt. If we modify it, we get I is equal to 1 by L integration of V dt, or we can get V by L, VL by L into T. This current equation, current through the inductor, has to be remembered. This equation will be helpful in when we try to determine the value of inductance, which will be more suitable. Now let us look at buck converter and how we can design this inductor in buck converter. We have already determined these two equations when switches are on and off from the current voltage relationship. So we can consider del IL equal to Vi minus V naught divided by L into dt. Why dt? This dt comes from the fact that switch is on. In this case, del IL would be equal to minus V naught by L 1 minus d t. 1 minus d comes from the fact that switch is off. Now for continuous conduction mode, we are designing it. So IL minus half of del IL will have to be greater than or equal to 0. If that is the case, IL, in this case we can see that no matter whether the switch is on or off, the output current, I output, will be equal to the inductor current, IL. So we can write IL is equal to I output, and del IL, we can write del IL as either this or this. Now here we see del IL is dependent on both input and output. So this will, using this for calculation, will give a complicated result. As a result, we use this expression. So we get V output by L 1 minus d t greater than equal to 0. One thing is to be noted that you can observe we haven't used the negative sign. Why we haven't used the negative sign? We already have a negative over here. So we did not, we have already compensated for that negative term, for the negative slope. Now we can write I output is greater than equal to half of V output. We can write as I output divided by I output R, V V output is I output R divided by L 1 minus d t. So here I output and I output gets cancelled out. As a result, we get L is greater than equal to R 1 minus d into t divided by 2f. Divided by 2. Or we can modify it as L is greater than equal to R 1 minus d divided by 2f. Here f is called the switching frequency. F is the switching frequency. That is, it depends on the time period of the switch that we are using, or the circuit that we are using. So from this, our value of inductor has to be greater than or equal to this value. So we can write our minimum value of inductor that we require is equal to R 1 minus d divided by 2f. So using this expression over here, we can actually determine the minimum value of inductor that will be required for this buck converter to operate. We can use an inductor of a greater value than this, no problem, but we cannot use inductor which has a value lesser than this. Now let us look at boost converter. In case of boost converter, by similar calculation, we get IL is equal to VI divided by L into dt since the switch is on, and again we get del IL is equal to VI minus V output divided by L 1 minus d t. So for simplification, we will be using this expression. As we have learned earlier, from continuous conduction mode, IL minus half del IL is equal to is greater than equal to 0. Now we can write IL as this. IL is the input current when the switch is on. IL is also the input current when the switch is off. So in this case, IL is equal to I input at all times is greater than equal to half del IL is equal to V input divided by L dt. Now the input output relations, we have found out that V output is equal to V input divided by 1 minus d, and again I output is equal to I input into 1 minus d. We have derived these expressions from current voltage relationships. So we can write I input as I output divided by 1 minus d is greater than equal to half. We can write V input is equal to V output into 1 minus d divided by L dt. So what we do is we can also write I output is equal to V output by R 1 minus d. As we can see, this is V output and this is our load R. So I output is equal to V output by R is greater than equal to half V output 1 minus d into dt divided by L. Now we can cancel this V output from both sides, and we get L is greater than equal to R into 1 minus d whole square into d divided by 2f. We write f is equal to 1 by t, or t is equal to 1 by f. We have replaced this equation here. As a result, we get this expression, which is from this we get minimum value of inductor that will be required to design this boost converter is R 1 minus d whole square into d divided by 2f. Thus, if we know this expression, we can calculate the value of inductor and we can design our boost converter. Now let us look at buck boost converter. The process is similar. Del IL will be equal to VI by L dt here, and del IL will be equal to V out by L 1 minus d t here. We can consider any of those for our calculations. Now for continuous conduction mode, IL minus half del IL is greater than equal to 0. So here IL is equal to I input when the switch is on. When the switch is off, IL is equal to I output. So we can write I output is equal to 1 minus d into IL, and I input is equal to D into IL. If that is the case, we are considering I output here. So we can write IL is equal to I output divided by 1 minus D is greater than equal to half del IL is equal to V output by L 1 minus D into T. So we can also write I output is equal to V output divided by R greater than equal to half V output by L 1 minus D T. Now V output and V output will get cancelled. From this we get L is greater than equal to R 1 minus D squared. This T we put as 1 by F. R into 1 minus D squared divided by twice F, where F is the switching frequency. So we get L min R 1 minus D whole square divided by twice F. So here we have determined the expression for buck boost converter, expression of designing this inductor. That's all for this lecture. In the next lecture, we will be learning about the inductor design for the other converters which require multiple inductors. Thank you so much.